So now that we've talked about linear alkanes, it's worth noting that carbon can actually orient itself into not just linear chains, but into cyclical chains as well. And so this cyclical chain of carbons would, under normal circumstances, if it was linear, we could actually count the number of carbons, 1, 2, 3, 4, 5, 6. So we could say that this would be a hexane if it was linear. But once we go from a linear to a cyclical structure, the name changes very slightly. So instead of hexane, this would be called cyclohexane. And in general, other cyclical variants can be named simply by changing the original linear name to having a cyclo in front of it. So, a 7-membered ring, if you could make a 7-membered ring, instead of heptane, it would be cycloheptane. 3-membered ring, instead of being propane, cyclopropane. Another very common way of talking about a cyclical carbon chain that you'll see a lot is going to be like this. So if we can have 6 carbons together, but we have a double, single, double, single, double, single, or kind of alternation, this kind of structure is so common it gets its own common naming. This molecule is called benzene. And we'll talk a lot more about benzene more toward the second semester of organic and a little bit in the first semester. But for now, let's talk about this cyclohexane molecule. So if we wanted to talk about hybridization of each one of these carbons, we could say that they would be sp3 hybridized. And so if you remember the geometry of an sp3 hybridized carbon, we said the optimal bond angle would be 109.5. But the angle that we actually have here would be 120 degrees if we subdivided the angles all in here. So if this cyclohexane was actually planar the way that we're drawing it on the board right now, if it was planar, this would be the angle, the internal carbon-to-carbon, carbon-carbon-carbon angle that we would see was 120, which deviates quite a bit from the 109 ideal. So instead of real-life cyclohexanes orienting themselves in a flat way, the way that the cyclohexanes actually orient themselves is what's called a chair conformation. And this is the way that the cyclohexane would look in real life, where it kind of looks like it's slightly puckered. So this is kind of pointing down, these carbons are up, these carbons are down, and this carbon is up right here. So with chair conformations, there are a couple of different ways that we can draw the substituents coming off of each carbon. So if we wanted to maybe number this carbon as carbon 1, we could talk about the implicit hydrogens that are coming off of carbon 1. So we really have HA and HB coming off of carbon 1, and these have their own specific orientations as well, and we can give them names. So carbon A, or hydrogen A, is what's called an axial position, and hydrogen B is what's called an equatorial position. And so the way you can distinguish an axial from an equatorial is that axial positions are either pointing vertically up or vertically down. So if we wanted to go from carbon 1 to, let's just say this is carbon 2, this carbon 2 also has 2 hydrogens on it. And we could say that these 2 hydrogens are oriented like this, where this vertical position is one possibility and this somewhat diagonal position is the other possibility. So because this is vertical, the fact that it's pointing down isn't really that pertinent, but the fact that it's pointing vertically is what's causing this hydrogen to be axial. And this hydrogen is also axial. This hydrogen is also axial. So we can not only call these axials, but we can talk about whether or not they're pointing up or pointing down. So we can say this hydrogen A is pointing up, so we would call this guy axial up. This hydrogen is pointing axial down, axial up, and axial down. An interesting thing to notice is that as we go around the ring, these axials are actually kind of inverting as we go from carbon to carbon. So you see this up, down, up, down kind of alternation. So the same thing is going to happen with equatorial. So if you look at hydrogen B is not vertical, it's kind of diagonal. And this hydrogen B is pointing diagonally kind of in a downward position. So we would call hydrogen B equatorial down. So just like as axial goes up and down in an alternating fashion, the same thing happens for equatorial. So this equatorial is going to be pointing equatorial down, that's an O, equatorial down, and so the next hydrogen over on carbon 2 is going to still be pointing equatorial up. Then the next one would be pointing equatorial down, and then the next one would be equatorial up. So this equatorial position alternates, just like the axial position alternates. And so now, if we wanted to talk about relationships between these hydrogens, we can call this A, B, and C, and then D. And what we can do is we can talk about the positioning of axial HA in relation to HC, and the positioning of HA in relation to HD. And if you look at HA versus HD, HA and HD, it looks like HA is pointing up and HD is pointing down. And since we have this relationship up versus down, we can give this a name. We call this relationship a trans orientation. So this is a trans orientation. And if you have HA pointing up and HC is also pointing up, the fact that it's equatorial doesn't really matter so much in this case. The relationship of HA to HC is what's called a cis orientation. So cis orientation. So the trans orientation is pointing basically in different directions, and the cis orientation is having two hydrogens pointing in the same overall direction. So if we wanted to, we could then say the relationship of HB to HC and HB to HD. And so since HB is equatorial down, we can say HD is also down. So HB to HD, this would be a cis orientation. And then HB to HC would be down and then up. So this would be a trans orientation. So going back to the original chair conformation, why do these molecules even go into this conformation? The reason they do this is that once you actually pucker the ring, you're able to get this red carbon, and every other carbon in the ring, to look a little bit more like it's in a tetrahedral form. So if you imagine maybe adding some stereochemistry or some three-dimensionality to this molecule, you could think about this bond going away, this bond coming towards, and these being in the plane of the paper. And so that looks a little bit more like a tetrahedron. So that's very close to that 109.5. So again, the overall impact of this puckering is that it allows the molecule to have an internal 109.5 degree optimal angle. So that's very close to that sp3 hybridized angle that you really want. So an interesting characteristic of the chair conformation, or the chair structures, is that once you actually make them go into this chair structure, they're not static. They're actually alive. They're dancing around. So they can do this interesting little maneuver called a ring flip. So this is actually an equilibrium between two different rings, and it's the same molecule, but it's kind of inverting itself. So this ring flip, you can think of it as an equilibrium. And so what's really going to happen is that if we look at this purple carbon and this red carbon, what's going to happen is after the ring flip, this purple carbon, it's kind of if you think about this purple carbon's orientation in relation to this white and this red, it's kind of pointing in an upwards angle. And after we do the ring flip, it's going to change from pointing up to pointing down. And if you think about the red carbon's orientation from this white and this purple, is that it's kind of pointing downward from both of these carbons. After we do the ring flip, this red will be pointing up. Okay, so what we've done is we've done the ring flip. And so again, what's happening is this purple goes from pointing up to pointing down. So it was pointing up, now it's pointing down. And the red carbon, it used to be pointing down, now it's pointing up. And so the question then is, what happens to hydrogen A, B, C, and D? Well, they're going to do basically a similar little flip. And so before, the HA was pointing axial up. And what's going to happen is after we do this ring flip, it's still going to be pointing up, but it's going to be flipped from an axial position to an equatorial position. So let me draw that out. We're going to have an axial and an equatorial, axial and equatorial, and this is going to be HA, and the other hydrogen is going to be HB, and for the red, we're still going to have an axial and an equatorial. Now, really quickly, how did I know to make this an axial up? The quick way around this is to think about this red carbon and its relationship between this white carbon and the pink carbon. So the white and the pink are making this red carbon look like it's kind of pointing in an upward direction. And so because of that, the axial position is going to be pointing in the same direction. So if this white and this pink make red point upwards, the axial will also point upwards. So right now, this carbon is pointing upwards, so the axial will also point upwards. This carbon is pointing downwards, so the axial will also point downwards. And the same thing here. This carbon is pointing downwards, so its axial will also point downwards. Okay. So now that we know that the axial is going to be pointing upwards, the equatorial must be pointing downwards. So here's our equatorial. So we have HA, HB, and we said that HA remains overall up. We're just changing the equatorial and the axial. So HA starts axial up, it ends up equatorial up. So the up doesn't change, axial and equatorial do change. So if HC is pointing up, at the end of the day, HC must still be pointing up. So this is HC pointing up. We've just flipped it from equatorial to axial, and at the end of the day, HD is still pointing down. It's just now flipped from axial to equatorial, HD right here. So in effect, what we've done is a ring flip, and we've actually been able to keep track of where all of our hydrogens are. So a lot of the times, students have a lot of trouble actually being able to see this. So what I'm going to do is I'm going to pause the video. I'm going to switch over to YouTube, a YouTube caption, and show you an animated version of this ring flip. And then after we see this, it becomes a lot easier to visualize. Okay, so here's the video we're about to start. But what you can see is this green plane. And if you wanted to identify an axial and an equatorial, maybe you could look at this carbon right here, and you can see this hydrogen is equatorial and this hydrogen is axial. And so what you're going to do, if you keep your eye on this carbon, you'll see how this equatorial switches from an equatorial up to an axial up. So keep your eye on the hydrogen right here. So you can see that the equatorial is flipping, 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 and now it looks very much like it's axial up. So I'll continue the video, and you can see that the overall ring is kind of puckering and changing, and you're going to do a flip right now. So then you go to the other side. So you can imagine this happening, but this is happening, you know, about a bajillion times a second. So the molecule is, again, not static, it's very active and alive.